Today, we're looking at section 6.4 in our textbook, and section 6.4 deals with confidence intervals for the variance and standard deviation. So we've talked a lot about confidence intervals here in chapter 6. We want to move on to variance and standard deviation now. They're a little bit different, but we start off the same way. So what is the standard deviation? Well, the standard deviation is the average amount by which the data set varies from the mean. Being able to control the amount by which the data set varies from the mean is important, especially in certain industrial applications where you're machining things like ball bearings or fittings that have to be a very precise size and specification. In that type of manufacturing process, we need to control the amount of variation. Just like the other confidence intervals we've talked about, we're going to start here with a point estimate. So when we're talking about the variance, sigma squared, the point estimate for sigma squared is the sample variance, s squared, right? So we saw that when we talked about the mean. We saw that when we talked about population proportions. The best way to find a point estimate for a population value is to look at the sample value. So that holds true here as well. When we're looking for the population variance sigma squared, the best point estimate is the sample variance s squared. Let's go ahead and look at the standard deviation sigma. For sigma, just like with the variance, we looked at the population value. We're going to look at the population value here. So the best point estimate for the standard deviation sigma is the sample standard deviation, S. Now, this is where it all kind of diverges from what we've done previously with confidence intervals. We're going to introduce a brand new type of distribution. It's called the chi-square distribution. Okay, so if the random variable x has a normal distribution, then as long as n is greater than 1, the distribution defined by chi-squared equals n minus 1 times s squared over sigma squared forms the chi-square distribution. So let's look at some properties of this chi-square distribution. First, all the chi-square values are non-negative. This is different from when we looked at the normal distribution. Remember, when we had z-scores, there were positive z-scores, there were negative z-scores. But with all chi-squared values, they're always non-negative. There's never any negative values for the chi-square distribution. Similar to the t distribution, the chi-square distribution is a family of curves defined by degrees of freedom, right? So it's not just one single curve, it's multiple curves, all depending really on the sample size, because the sample size is how we define the degrees of freedom. Just like the other distributions we've seen, the area under any curve in the family is equal to 1. But unlike the other curves we've seen, this chi-square distribution is non-symmetric and it's positively skewed. Another way to think of positively skewed is it's a skewed right distribution. That means it has a tail that goes off to the right. So what does it look like? Well, it looks kind of like this. So jumps up to a big hill and then gradually comes back down to a tail. Right, but notice it doesn't go to the negative side of the graph. It just stops right there at the origin. So because this is not symmetric, we're going to have to change the ways we find our critical values. When we would deal with the standard normal curve or the t distribution curve, we could find one of the z-scores or one of the t-scores, and we knew that the other critical value was going to be the opposite. So we would have plus or minus the same value, plus or minus the same value. But we can't do that here because there's no negative, right? All the chi-square values are positive. So we can't do plus or minus the same number. We have to come up with a brand new way to do this. So for a given level of confidence C, we have to find critical values that contain an area of C in the middle of the distribution with equal areas in each tail. This is what we did when we were dealing with the normal distribution. It was just easier for us because the normal distribution was symmetric, and we were using that symmetry to our advantage. when we find these values that have that area of C in the middle with equal areas in the tail, we'll call those our chi-square values. And there's going to be one on the left side and one on the right, so we'll call them chi-square L and chi-square R. If they're right here, let's say, and we were to draw a vertical line up until it hits the curve itself, that area in the middle would be C. And then the areas in the tails would be 1 minus C if you combine them. And so for each one, it's 1 minus C divided by 2, because remember, we said we wanted them to be equal. The whole area under the curve is 1. If C is in the middle, then the two tails combined have to be 1 minus C. And because we want them to be equal, that means we want each one to be half of that. So we divide by 2, and that's how much area is in each part of the curve. Now this chi-square distribution has a table of values, and we've seen a table of values for the standard normal distribution. We've seen a table of values for the t distribution, and this chi-square distribution is no different. It has a table of values. It works a little differently, but it is still a table of values. It has one major difference though, and in all the tables that we looked at before, we were always finding area to the left, but in the chi-square distribution, we're using area to the right. I don't really know a good reason why we set up the table that way. It is actually possible to redefine this table and set it up the other way. I've never really found a good answer to that, but that is how it is done. So this table has area to the right. So here's what that chi-square distribution table looks like. It's a big one. Okay. We have our degrees of freedom down the left-hand side and our value of alpha in the top. Now, we'll explain exactly what that is here in a few moments, but we're going to be looking at multiple columns to find our critical values, not just one column like we did before when we're using the standard normal distribution. It's a pretty lengthy table, and actually you can find longer versions of this table in other textbooks and online. So let's do an example. We want to just find the critical values. We're not even talking about confidence intervals yet. We just want to find the critical values, be able to look at the chi-square distribution graph and the table and come up with the two values we need when we have a 95% confidence interval and a sample size of 24. So let's try to draw the picture, because I think that picture really helps when we're trying to determine these values. So here's what our picture looks like. Remember, we want the confidence interval, that size, to be the area in the middle. So because we had a 95% confidence interval, we want 0.9500 in the middle. Well, if there's 0.9500 in the middle, then that means the two tails combined have to add up to 0.0500. And because we want to have the same area in each tail, we divide 0.0500 by 2, and that's where the 0.0250 comes from. If you add those three numbers up, you see that they add up to 1. So then we're going to ask ourselves a few questions. Okay. Let's keep that graph up there so that we can see it as we answer these questions. What is the area to the right of chi-square L? Okay. So if we look to the right of chi-square L, it's 0.9750. How did we determine that? If we look up here on the graph, you might see my cursor on the screen. We're coming from this chi-square L value, and we're going to the right. So how much area is under the curve to the right? Well, we have this 0.9500, and also this right-hand tail, 0.0250. And if you add these two together, that's where this 0.9750 comes from. All right, well, what about the area to the right of chi-square R? Right? So if we, again, go to the graph of the chi-square distribution, we find the chi-square R here over on the right-hand side. We want to know how much area is under the curve to the right. Well, that's just the right-hand tail. So that's just this tail area of 0.0250. We also need to know the degrees of freedom in this problem, and the degrees of freedom are directly related to the sample size. The sample size was 24, so the degrees of freedom here are 23. Remember, degrees of freedom are n minus 1, the sample size minus 1. So let's look at the chi-square distribution table. So I put a little cutout of the table here for you. We're looking for those two area values that we found as our alphas. That's what the alphas represent. They represent the areas to the right of our chi-square values. So when we go to 23 degrees of freedom and 0.975 as the alpha value, we get to this 11.689 value. That is our chi-square L value. When we go to the 0.0250 on top, we come up with a value of 38.076. Those are our critical values for chi-square. So chi-square L is 11.689, chi-square R is 38.076. Okay, so how about a practice problem? So I want you to do the exact same kind of thing, just finding the critical values. We're not doing anything else with them. And your setup is you want to find chi-square L, chi-square R for a 90% confidence interval when the sample size is 15. So go ahead and press pause on your computer, and when you're all ready to go, press play. Okay, so let's go ahead and take a look at the solution here. We're going to look at a picture just like we did in our example. This time, in the middle, we have our confidence value, which is 0.9000. So the area under the total curve is 1, so if we do 1 minus 0.9000, we get 0.1000. Divide that by 2 so that we can equally disperse that area into both of these tails, and each tail will have an area of 0.0500. So now that we've got this picture in mind, we want to ask ourselves those same questions as we did in the example. What's the area to the right of chi-square L? So if we look on our graph, we go to the right here. There are two regions to the right of chi-square L. There's the central region that has an area of 0.9000, and the right-hand tail that has an area of 0.0500. So the area to the right of chi-square L is going to be 0.9500. What about the area to the right of chi-square R? Well, when we look up at that diagram, chi-square R is right here. The only thing to the right of chi-square R is the right-hand tail, and the area of the right-hand tail is 0.0500. We need the degrees of freedom. In this problem, since our sample size was 15, our degrees of freedom are 14. So now that we've got our degrees of freedom, we can turn to the chi-square distribution table. And so we look for our area values under the alphas at the top. So for 0.9500, we just find 0.95. Remember that zeros at the end of a decimal are extraneous. We can leave them off. And for the chi-square R value, 0.0500, we're just going to look for 0.05. So when we go down to 14 degrees of freedom, under the 0.95, our first critical value, that chi-square L, is 6.571. And we go to the column for 0.05. We go down to degrees of freedom equals 14. And our chi-square value is 23.685. So that gives us our two critical values. So now we come to a very striking difference between the confidence intervals we've done before and what we're going to do here for the variance and the standard deviation. We are not going to find a margin of error. That's what we used to do for the mean and for population proportions. But because of the way that the standard deviation and the variance are both computed, that doesn't make sense here. So there's a whole other way that we go about it. We're going to use these critical values to create upper and lower boundaries. It's all about asymmetry, right? If we had a nice symmetric distribution like a t-distribution or the normal curve, then we would be able to do plus or minus a value. But because we don't have that symmetry, where we can say, oh, look, on this side the tail is exactly the same as that side. We can't do plus or minus to get to that correct value to get us the tails that have the same area. So how do those confidence intervals work? Well, let's start with the variance, sigma squared. The confidence interval for the variance is given as an inequality. So sigma squared is right in the middle of n minus 1 s squared over chi square r and n minus 1 s squared over chi square l. Then, for the standard deviation sigma, we have that same formula, but now we take the square root of everything, right? Because remember, we have the relationship between the variance and the standard deviation that says that the standard deviation is always the square root of the variance. So we take the square root of each portion of that formula above, and we get the square root of n minus 1 times s squared over chi square r with sigma in the middle, and then the square root of n minus 1 s squared over chi square l with the square root. So with these formulas, what I want you to notice is that the right-hand critical value for the chi-square distribution is on the left side of the distribution, and the left-hand critical value is on the right side of the distribution. Now, why would this be the case? So when we look at this fraction, the chi-square r value is on the left, and remember that the chi-square r value is larger than the chi-square l value. So that means that this fraction, because we're dividing by a larger number, this fraction on the left is a smaller number. When you divide by a large number, that makes the value of the fraction smaller. On the right, since we're dividing by chi square l, which is smaller, when we divide by a smaller number, that fraction ends up being larger. And that's always the case with these fractions. The chi square r will be on the left, and the chi square l will be on the right. So that's kind of contained in our note here. In the formulas, the left critical value is on the right side of the formula, and the right critical value is on the left side of the formula. Let's take a look at an example. A manufacturer of wheel bearings takes a sample of 26 bearings and measures their diameters. The sample had a standard deviation of 0.07 millimeters. Assuming the diameters are normally distributed, construct a 98% confidence interval for the population standard deviation. So if you've ever looked at wheel bearings in a car or in some other cart or something like that, where you have these tightly packed wheel bearings, they have to rotate around each other freely. And if the size of these bearings was off by too much, they would lock up and the entire wheel would actually stop turning. So you have to make sure that the amount of variation in the manufacture of these wheel bearings is very, very slight. Okay? So you have to be able to control the variation. Otherwise, you have a problem. Let's take a look at our solution. We'll start by looking at what the distribution looks like. So with the confidence interval of 0.9800, that's going to be the area in the middle of our chi-square distribution, which is going to leave an area of 0.0100 to each side, right? Because the total area underneath the curve has to equal 1. So we would take our confidence interval, which is C, subtract it from 1. 1 minus 0.9800 is 0.0200, and divide that in half so that each tail has an equal area. So we'll ask ourselves the same questions as before. What's the area to the right of chi square L? So if we go up on the graphic and we look for chi square L, we go to the right, we have these two areas, 0.9800, 0.0100, which gives us a total of 0.9900. Then if we go to the right of chi square r, here's our chi square r, the area to the right of chi square r is just this right-hand tail, 0.0100. If you haven't noticed, the two areas that we get, the area to the right of chi square r and the area to the right of chi-square L will always add up to 1, because the first area, the area to the right of chi-square L, is going to be the central region plus 1 tail. And then the area to the right of chi-square R is 1 tail. So that means the total here would be the central area plus 2 tails, which would be the entire distribution, because we carry the same area in each tail. What about our degrees of freedom for this problem? Well, in this problem we had 26 bearings, so our sample was size 26, which means the degrees of freedom are 25. So let's go ahead and take a look at our chi-square distribution. We look for 0.99 and 25 degrees of freedom, and we come up with a chi-square L value of 11.524. And then we look at the 0.01 and 25 degrees of freedom, and we get a chi-square R value of 44.314. So now we've found our 2 critical values, but we want to go further. So now we want to find the actual confidence interval. And we have our formula. Remember, sigma is right in the middle of 2 fractions that are underneath square roots. So sigma is between the square root of n minus 1 times s squared over chi-square r and the square root of n minus 1 s squared over chi-square l. And again, the right-hand critical value is on the left of the formula. The left-hand critical value is on the right of the formula. So we have all these values. We can just go ahead and plug them in. So look at what this formula calls for. N minus 1. That's the degrees of freedom. So our degrees of freedom for this problem was 25. S squared. Well, we know the value of S because in our original problem setup, it told us that our sample standard deviation was 0.07. So we're going to have 0.07 squared. And then we just found the chi-square R and the chi-square L values. So we've got our 25 times 0.07 squared over 44.314, the square root of that fraction. Remember, the 44.314 is our chi-square R value. Then on the right-hand side, notice that the numerators are completely the same in these fractions, and that's always the case. But in that fraction on the right, we have the left-hand chi-square L value in the denominator, 11.524. So if we plug those into our handy-dandy calculators, we end up with sigma is stuck between 0.0525772138 and 0.1031018409. If we round off to 3 decimal places, that's 0.053 and 0.103. So that's our confidence interval. And we can write our confidence intervals in that interval notation that we had when we were talking about the mean and the population proportions, where we just put the left one and the right one in a parenthesis separated by a comma. So we can still write our confidence intervals in the same way, they just don't quite work the same. Because if you remember what our point estimate here was, the point estimate here was 0.07, right? That was the sample standard deviation that we got when we were looking at this problem. 0.07 is not right in the middle of this confidence interval of 0.053 and 0.103. Okay? And that's because of the nature of the square root. When we take square roots, it doesn't preserve distance between numbers, so we don't end up with a nice symmetric confidence interval here like we would before. So what does this confidence interval mean? It means that we are 98% certain that the population standard deviation is between 0.053 millimeters and 0.103 millimeters. Okay. Now, is that good enough for the manufacturing process? I'm not sure, right? We would have to check with the manufacturer to see what their actual tolerance for difference would be. But that's what the answer is for this particular problem. We have a little note here. And the note says the point estimate for sigma does not fall in the center of the confidence interval for sigma, right? We just saw that where the 0.070 doesn't fall in the middle of 0.053 and 0.103. It's in there, but it's not exactly at the center. So how about a practice problem? A manufacturer of vitamins takes a sample of 17 vitamin C tablets and measures their weights. The sample had a standard deviation of 1.01 milligrams. Assuming the weights are normally distributed, construct a 95% confidence interval for the population standard deviation. So this is just like the example problem we just did. So go ahead and work on that. Press pause on the video. And when you're ready to see the answer, press play. Okay, so we're going to do this just like we did that example. We want to look at a picture because we want the 95% confidence interval. We've got the 0.9500 right in the middle with two tails. Each one is 0.0250. We ask ourselves the question. We start with the chi-square L value. What is the area to the right of chi-square L? So when we look on our picture, we find the chi-square L. The area to the right is going to be these two regions, the 0.9500 area and the 0.0250. When we add those together, we get 0.9750. When we look for the area to the right of the chi-square R value, that's just the right-hand tail, which is 0.0250. And remember what we said, that these two areas will always add up to 1. What are our degrees of freedom? Well, we took a sample of 17 vitamin C tablets, so that means that the degrees of freedom are 1 less than that, which is 16. We're going to go ahead and consult our table now. We find the 0.975 value for alpha, and that gives us a critical value of 0.6908. When we find the 0.025 value, that gives us a critical value of 28.845. So those are our chi-square values. Chi-square L, 6.908. Chi-square R, 28.845. We can go ahead and use our confidence interval formula now. So remember that sigma will fall between two fractions, each of which is under a square root. So on the left we have the fraction n minus 1 times s squared over chi-square R under the square root. And on the right we have n minus 1 times s squared over chi-square L under the square root. So the n minus 1, that's our degrees of freedom. The s value here was 1.01. And then we have our two chi-square values. So we're going to have 16. So with each one of these fractions, we're going to have the same numerator. N minus 1, which is the degrees of freedom, 16, times the s value, which we knew was 1.01, squared. That's our same numerator for both fractions. In the left-hand fraction, we're going to have chi-square R, which is 28.845. In the right-hand fraction, we're going to have chi-square L, which is 6.908. We use our calculators, and we figure out that the left-hand fraction is 0.7522221083, and that the right-hand fraction is 1.537110.894. If we round this off, we get 0.752 and 1.537. And if we wrote that in our standard confidence interval form, 0.752, comma 1.537. So what does this mean for us? This means that we're 95% certain that the population standard deviation is somewhere between 0.752 milligrams and 1.537 milligrams. So that brings us to an end of section 6.4. Please look for your homework on Pearson, and have a nice day.